thank you very much for the invitation to give this course here. It's a great honor and pleasure to give the Cours Peccot. I was told that the first lecture should be for a general math audience. I see 2-3 experts in the audience. You can just sleep or do your own math. So it's not aimed at you, but at the general audience to bring everyone up to speed. And in general, I try to make these courses accessible. So I was just told that the first course was announced a bit late, but it will be recorded. So those who are interested, well, who are not here, that doesn't make sense to tell this to you, but to the people at home, can watch that before the next lecture so that hopefully the whole course is accessible. Feel free to interrupt and ask questions at any time. Just to make sure, not everyone is an expert here, is that correct? Okay, excellent, good. All right, so the one thing, when I was a grad student, I gave my first colloquium talk and asked my advisor if he has any recommendation for what to do, and he gave me precisely one piece of advice, which is make sure to define the p-adic numbers. And when I talk with colleagues in PDEs, they often also ask me questions about what are the p-adic numbers, what is the characteristic of the p-adic numbers. So let's start by introducing the p-adic numbers, because, well, my talk is about representations of p-adic groups. So we need to first understand what are the p-adic numbers, then what are the p-adic groups. And so maybe just to give you an overview, today I will first introduce p-adic numbers, p-adic groups, and then tell you what are representations of p-adic groups. And then give you an overview of what's the state of the art and hint a bit in the direction that this course is going into in the next few weeks. So, what is P? P is a prime. And hopefully I'm not falling off the stage. So what are the p-adic numbers? So first section, p-adic numbers. So here's a definition. So let n be an integer and write n as p to the r times, oh, well, I said integer, but we can also take a rational number. And then we can write n as p to the r times a over b, where a and b are co-prime to p. And then we can define the p-adic absolute value. So the p-adic absolute value, if I'm writing too small, don't speak loud enough, just interrupt and ask. The p-adic absolute value of n is, well, I noted by the standard absolute value sign, which is small p, is defined to be p to the minus r. So that means the p-adic absolute value measures how often a number, an integer or rational number, is divisible by p. And the more often the number is divisible by p, the smaller the absolute value. So for example, just so that we see some example, the p-adic absolute value of 1 is just 3 to 0, so that's just 1. The p-adic absolute value of 3 is 1/3. The p-adic absolute value, of 9 is 1/9, and so on. So the more often the number is divisible by 3, the smaller the p-adic absolute value, and so the p-adic absolute value of 10 is just 1 again. All right, so that means the p-adic absolute value measures how often a number is divisible by p, and that allows us to define the p-adic numbers. Can you see all the way to the bottom of the blackboards? Excellent. So the p-adic, well, there are two versions, integers and numbers. Let's say the p-adic integers, or numbers, I'm defining both at the same time, are the completion now of the integers or the rational numbers with respect to this p-adic absolute value. So p-adic integers or numbers are the completion of either the integers, the standard integers, or the rational numbers with respect to this p-adic absolute value. So you might have all seen the real numbers, which are just the completion of the rational numbers with respect to the standard absolute value, and now the p-adic numbers are the completion of Q with respect to this new weird p-adic absolute value. And so what does it explicitly mean? It sounds a bit abstract. Explicitly, this means a p-adic integer is of the following form. So we can just write it as a power series in P. So it's of the form A0 with A0, so all the AIs being some numbers between 0, 1, 2, up to P minus 1. And so we can write every p-adic integer the form A0 plus A1 times P plus A2 times P squared plus and so on, and go off to infinity. So if we stop after finitely many steps and add these numbers, we just get a regular integer. And if we go to infinity, this series will converge because the absolute value of p to the n is p to the minus n, so we'll approach 0. So you can think of p-adic numbers as power series in P. And sorry, that was a p-adic integer. If we want to get the p-adic numbers, so the completion of Q rather than of just the integers, then it's of the same form, except we allow some negative exponents. So we start with a minus n to the p to the minus n plus, and so on, plus a0 plus a1 times p. So for some integer n, or natural number. So that means when we want to talk about the p-adic numbers, which is the fraction field of the p-adic integers, we allow negative exponents, and the p-adic integers are the ones with non-negative exponents only. So that, if you see it the first time, you might wonder, so what is this? It's an interesting way of building a new field, or a new ring, or a new field from the rational numbers, or the integers. And I want to show you how this actually looks like. So I want to show you the example of the three-adic integers and try to picture them, try to draw a picture. So, well, let's just start with the regular integers and let's try to understand this absolute value. So there's the integer 0. Sorry, for me 0 is an integer. Positive, well, for you it's positive, sorry. So let's look at positive. So there's 0, 1, and 2. All these three non-negative for me integers have distance 1. So the three-adic distance between these two is 1. The same here and the same here. So the three-adic valuation of 2 minus 1 is, well, the three-adic valuation of 1, which is equal to 1. And that corresponds basically to choosing A0 to be 0, 1, or 2. And now if I keep going, so the next integer would be 4. What is 4? 4 is, 3. I can't even count. The next integer after 2 is 3. What is 3? 3 is 0 plus 1 times 3. And the distance to 0 is 1/3. So where is it? It's roughly here. So the distance here is 1/3 because the difference is divisible once by 3. And then the next integer is 4. Where is 4 located? It's somewhere located here. The distance to 1 is 1/3, and the distance to everything else, so to 2, for example, is still 1, and the distance here to everything else is 1. So that means we can keep playing the game. 4, the next one is 5. 5 is somewhere located here, has distance 1/3 to 2. Now this picture gets very cluttered, so let me maybe see if I can start one again without the arrows. So we have 0, 1, 2. Then we have 3, 4, 5, 6, 7, 8. And you might get the pattern. So everything in here has distance 1/3 from each other, and 2 different blocks have distance 1. And now if I add 9, 9 is very close to 0. So 9 would be very close here. That's 9. 10 is very close to 1, and so on. So if I keep going, that means each of these dots gets subdivided into 3 smaller dots. And then I hope you get the idea. I can keep going, and around each dot I add smaller and smaller and smaller and smaller dots. So that's how the p-adic integers look like. So I take just the regular integers, but rather than drawing the regular integers on the real line where we have 0, 1, 2, 3 nicely spaced, I obtain something that looks very, very different, and that's the outcome. So it looks like a fractal. So this is what the p-adic integers look like. It's like a weird fractal. So let me write this down maybe as some properties. So properties of the p-adic integers and the p-adic numbers. Well, they look very different from the real numbers. They look like this weird fractal here. So that means the topology is totally disconnected. So it's, even though it's also a completion of Q, so let me write this down as well. It's a completion of the rational numbers, sorry, I said rational, of the rational numbers with respect to this weird p-adic norm rather than the regular absolute value. So it's very similar to the real numbers, but the topology, the picture looks very, very different. So that's the p-adic numbers. They are usually written as z sub 3, and these are the real numbers. So you see they look totally different. Let me add that here. So the p-adic integers, because I might use that later, they are usually denoted by zp, so integers with a small p, and the p-adic numbers that we obtain from Q are denoted by Q sub p. So that's what the p-adic numbers are. They are just the completion of Q, but they look very different. They are totally disconnected. So there are a lot of parallels to the real numbers, but there's also a crucial difference, which is this topology, this totally disconnectedness. There's another crucial difference, which is if you look at the real numbers, say under addition, there are no compact subgroups other than the trivial one. But here we have tons of them. So there are infinitely many compact open subgroups of the p-adic numbers, say under addition, but the same works for multiplication. And so here are some examples. So zp itself is compact. So this, what I've drawn here, is zp. It's z3. That's something compact. Inside there, I can take p times zp, and that's also compact. So p times zp would be just the subgroup down here. Inside there, I can take a smaller subgroup, p squared zp. That's another compact subgroup, and p to the whichever number you like, 17 zp. All these are compact open subgroups. I can take also p to the minus 17 times zp, also a compact open subgroup. So I can take smaller and smaller circles around the identity 0 and get tons of compact open subgroups. In particular, I get basis of neighborhoods that way. And that will be very important when we study p-adic groups. All right, so that's the p-adic numbers. That's the p-adic in p-adic groups. There is a closely related field, which is, let me call it a sister field, or brother field. What is the sister field? The sister field, the Laurent series, or sometimes we'll say formal Laurent series, I can't write anymore, series, over a finite field. Over a finite field, let's say with p elements, so fp with p elements. And what is this? The Laurent series over a finite field with p elements. It's written as fp double brackets t. T is the formal variable. And this is just defined to be essentially the same as here, these power series, but now in a formal variable instead of t. So this is just t to the minus n times some coefficient a minus n and so on, plus a0 plus a1 times t t plus a2 times t squared. And we are allowed to go off to infinity, again, where n is some integer, you can still see. And now the coefficients are elements of a finite field with p elements. So that's essentially roughly, again, 0 up to p minus 1, except that's now a field. So they behave very similar. What is a key difference? So a key difference, I said at the beginning, I'm often asked, what's the characteristic of the p-adic numbers? And I haven't told you yet. So the characteristic of the p-adic numbers, let me add this here. The characteristic is 0, because the p-adic numbers, they contain q, and z, I mean, all the integers are contained in there, and none of them is 0, so none of the prime numbers is 0 in the p-adic numbers. In particular, p is different from 0. However, in the sister field, this formula series over a finite field, the number p is actually equal to 0, because p is equal to 0 in this finite field. So p occurs as this a0 and is the same as 0. So the sister field of formula series here has characteristic p, because p is equal to 0. Let me add one more thing. I'm afraid you might not see down there. The sister field is very similar to the p-adic numbers. You see already the structure is essentially the same, except you replace p by a formal variable t. And so we also have a p-adic absolute value on this field, and the p-adic absolute value of, say, t to the s times a0 plus a1t, and so on, where this is non-zero. The p-adic absolute value is just p to the minus s. So I factored out all the t's that I can factor out, and that's giving us the absolute value. So again, the p-adic absolute value is smaller the more often the number is divisible by t. That's the same as for, I'm repeating essentially the same as what I've done for the p-adic numbers. I just replaced p, which there was a real integer, by just a dummy variable t. Otherwise, it's the same. And so these two fields, they are very closely related, and they are called local fields. So let me, just so that if you see the notation out in the world, you know what it is. A non-Archimedean local field is a finite field extension of either the p-adic numbers, so either of qp, or of these Laurent series of fp double brackets t. So that's what people refer to as a non-Archimedean local field. A local field would be a finite extension of qp or fp double brackets t or the real numbers. So local fields include the real and the complex numbers. And non-Archimedean local fields are only these extensions of qp and fp double brackets t, which are the ones that have a non-Archimedean norm on it. So this, the absolute value is non-Archimedean here. All right, you can forget this word again, because I will not use it. But if you see it out in the world, you know what it means. So, but from now on, the following notation will be in place. I will denote by f either a finite extension of qp or f is a finite extension of these Laurent series. i.e., in other words, f is a non-Archimedean local field. So in particular, if this is the first time you see p-adic numbers in Laurent series, just think of the p-adic numbers themselves. Or if you're more familiar with Laurent series, some people work with them where they replace the finite field by complex numbers. Feel free to just think of that field and take your favorite field. All that I'm going to talk about works in all cases. All right, so that's the field. Now I promised you that we want to figure out what are p-adic groups. we already know what this p-adic now means. That refers to the p-adic numbers, but equally well to these formal Laurent series. What are p-adic groups? Well, let me give you a kind of fake definition that I think is the best to work with. A p-adic group is the analog of a Lie group, but over this field F. So this is a bit confusing maybe, so I really want to give you examples and do this whole thing via examples. So for example, we can use GLN of F, or well, a sub-example would be just GLN of QP, or GLN over these Laurent series over a finite field. So GLN means n by n invertible matrices. So that's something rather explicit. Like just take n by n matrices, and for real Lie groups you would take n by n matrices over the real numbers, but for p-adic groups you take n by n matrices over one of these fields that I've introduced. So that's one standard example to keep in mind. Another example would be SLN. So these are the matrices of determinant 1. So that's a subgroup of GLN. Another classical example would be SON, which are all those matrices of determinant 1 that preserve an inner product. So those matrices that preserve an inner product, they form SON, the orthogonal group. And I give you one more example. And I'm also going to tell you the official definition, but that won't help you at all. Well, unless you know everything already, and then you don't need to be here. And the final example is SP2N. These are all the matrices as above that preserve a symplectic form. So in terms of matrices, you could write SON as matrices of the form A such that transpose A times A is the identity. And you have a similar description here where you say that transpose A, J, A is equal to J, where J are just matrices with ones on the off diagonal. It's a very explicit way to say that these are all the matrices A inside GLN or SLN that have that property. So if you haven't seen p-adic groups before, really the best thing is to think of one of these examples. Think of GLN, SLN, SON, and SP2, and ideally all together. So these are just nice subgroups of GLN. There are two more things I want to say. Another example is you take products of the groups above. So for example, you take a product of GLN with SP2M or something like that. And then there are also all kinds of exceptional groups. So it's really the same way as for Lie groups. If you have studied Lie groups, you know that there are these root systems, and so you can classify them, and there are weird things like G2, E6, C7, E8, and these things. The same appears in the p-adic world, but really, if it's the first time, think of one of these classical groups I've written down. If you're familiar with the notion, let me say that the precise definition that I'm working with is that a p-adic group are the F points of a reductive group, of a connected reductive group. And I want to assume our group splits over time extension. That's just to make my life easier. I can give you the definition of reductive group. Reductive group means it's a linear algebraic group. So a closed subgroup of GLN whose unipotent radical is trivial. And believe me, no one in our area works with this definition anymore. I mean, this is the official definition, but what we really do is we start with this definition, and then there's a lot of structure theory that tells us about the structure of these groups in terms of so-called tori and root groups, and that's what we really work with. And that's the same as saying, just think of GLN, where we have diagonal matrices, upper triangular, lower triangular matrices, and that's just what we abstractly obtain also in the general setting of reductive groups. So really, if this is the first time, think about these groups, and you will really get the whole message of this talk. Okay, so that's what a p-adic group is. Let's see, did I want to say, I think I wanted to say a few properties. Yeah. Or let me ask, are there any questions so far? So I'm erasing the first picture. Let me keep the second picture of the p-adic numbers to talk about some of the properties. So what are these properties? So I said it's like real Lie groups or complex Lie groups just over these p-adic numbers. And these p-adic numbers are similar to the real numbers. It's a completion of Q. But we observe they are totally disconnected. So something is different there. And so the topology on these p-adic numbers, so when I say p-adic numbers, I also mean Laurent series. So p-adic groups also includes the case over Laurent series over finite fields. So the topology on this local field F gives us a topology on the group, on our p-adic group. So let me maybe introduce some notation. Let G be a p-adic group. So for now on, G is always a p-adic group. For the experts, one that's split over a time extension. And then the topology on the group, on the field F gives us a topology on the group G. And so this topology has a bunch of nice properties, in particular since the topology of F is totally disconnected. The same happens for G. So this is, gives as a totally disconnected group, and the topology on G is given by a basis of neighborhoods. So I can write it down explicitly, and the nice thing is that this basis consists of subgroups. So topology on G is given by a basis of open neighborhoods consisting of compact open subgroups. And let me make this very explicit. So let's take GL2 of QP. You can also take GLN of F. You see immediately how to generalize it. It's just easier to write GL2 on the blackboard. Inside there, we have GL2 of ZP. That's a nice compact open subgroup. Inside there, we have all the matrices of the form 1 plus PZP on the diagonal and PZP off diagonal. So that's a smaller compact open subgroup. Inside there, we have 1 plus p squared ZP, 1 plus p squared ZP, p squared ZP, p squared ZP. And if I write matrices like this inside GL2, I mean they are invertible. Inside SL2, I mean they have determinant 1. And so you see the pattern. We can keep going. So in particular, all the subgroups in here, we have all these subgroups of the form 1 plus p to the n ZP on the diagonal and p to the n ZP on the diagonal. And these matrices, they get smaller and smaller and smaller, and they form a basis of the identity consisting of open compact subgroups. And that's how the topology can be defined on GL2, and you can do the same with GLN, just all the matrices congruent to 1 modulo p to the n. That gives you a basis of open neighborhoods. And let me remark that this is actually what leads to so-called Moy-Prasad filtration. One can generalize that to obtain the Moy-Prasad filtration, which is an important tool in the construction of representations of p-adic groups, and that's something we will study in this lecture series, not today, but in the next few weeks. So that was one remark. Another remark is that, so if you're familiar with real Lie groups, complex Lie groups, you know that there's always, well, they're compact open subgroups. They're maximal compact open subgroups. They are not unique, but they are unique up to conjugation. So in the Lie group setting, they are essentially unique. They are unique up to conjugation. And this breaks down in the p-adic setting. So the maximal compact subgroups are not always unique up to conjugation. And that makes this subject so much more interesting because there are all these different compact open subgroups that we have to understand that are maximal but not conjugate. So for example, if our group G is SL2 over, say, QP, can also take SL2 over F, any field, then the compact maximal compact subgroups up to conjugation well, the one is just SL2 over ZP, and the other one is you just take matrices of the form ZP on the diagonal. Well, if I put ZP everywhere and say determinant equals 1, then that's just SL2 over ZP. But if I instead, what I can do is I can scale the upper corner by P and the lower corner by P inverse. And this subgroup is also a maximal compact subgroup. So maximal comes first. But it's not conjugate to SL2 over ZP. It's only conjugate over GL2, but not over SL2. So that means we have here suddenly two different maximal compact subgroups. And the study of these maximal compact subgroups, that's what's called essentially Breuer-Tietz theory. So Breuer and Tietz, they introduced the notion of a Breuer and Tietz building that studies, that tells you how to find these maximal compact subgroups. And that's another topic I will touch on in this mini course. Again, not in details today, but in the future lectures. All right, so I introduced what the p-adic numbers are, what the p-adic integers are. I introduced the sister field that I just erased, which is very similar. Then I introduced the p-adic groups, which are just Lie groups essentially over these fields, over these finite extensions of either QP or the normal series or a finite field. And I told you they have, well, something in common with Lie groups, but also something, some interesting features like these filtrations by compact open subgroups that become smaller and smaller and smaller, and that these the maximal compact subgroups are not all conjugate. So now we know what p-adic groups are. I hope we have a bit of a feeling for it, just GLN over a p-adic field, essentially. Now I want to tell you what are the representations. So we dive into representation theory. Let's see. Here we go. What is a representation? So a representation of G, as I said, G now from now on denotes a p-adic group, so that's the main object that we want to study, and we want to study the representations thereof. So representation of G is a pair, which is often written as pi and v, and I might drop pi or v sometimes and just write one of the two, consisting of, well, what is v? V is a complex vector space. And in math, you can always vary all the things that appear in statements. So one thing you could vary is you can replace complex by some other field here, and then you get a different theory. But let me focus here just on the complex numbers for simplicity. So it's a complex vector space, V together with pi from G to the space of automorphisms of this vector space. The C-linear automorphisms is a group homomorphism. And so this is what it means to be a representation. That's something that you might have learned in your first algebra or second algebra class. It's just a group homomorphisms from an abstract group into the space of linear automorphisms of a complex vector space. Now, since we work with G being a p-adic group, we know that there's some structure to it. We know there's this topology on it that makes it totally disconnected, which has all these nice properties. So I want to take this into account. So I add the word smooth. And I want to consider only smooth representations. And the smooth representation is one such that the following happens, such that for every vector, small v inside capital V, there exists some compact open subgroup of G. So K is a compact open subgroup of G, and there are plenty, as we have seen, such that this compact open subgroup fixes the vector V. So such that if I take pi of K, that's an automorphism of the vector space. If I apply this to V, I get back V. And that should happen for all small k inside capital K. So that's what it means to be smooth. Smooth means every vector is fixed by some compact open subgroup. So there's something rather large that fixes every vector, and therefore we get some reasonable category that we can work with. And all representations from now on will be smooth. So I might not write smooth all the time, but they are always smooth. And so that's what we want to study. We want to study these smooth representations. So here's our first goal. Before I write this goal down, let me write one more property. So the goal is that we want to understand all these representations. But here's one nice thing. There are certain building blocks for these representations, and I will define for you what they are and what that word means, building block. And they are called supercuspidal representations. So these are the building blocks. As I said, I will define that. But for now, just consider them as building blocks. And then our first goal for, when I say goal, it means goal for mathematicians for the last 50 years, as well as goal for us to understand in this lecture series, is to construct all these supercuspidal representations. So construct all supercuspidal representations of our given group G. So that's a big goal. A lot of mathematicians have worked on this, and we are close to finishing that goal. Under minor assumption, we can actually do that. Why do we care about this goal? Well, one reason is it gets you invited to give a talk series here, which is pretty awesome. But also, there are tons of applications of that. So let me just mention a few applications. Well, there are the obvious applications to the representation theory of p-adic groups. So if you want to study what happens when you take a representation of a p-adic group and restrict it to some subgroup, or if you want to study different correspondences that occur in this theory, for example, the Howell correspondence, and understand how do representations get transferred from one group to another group. If you want to calculate character formulas, for all these things, if you want to do this explicitly, you need to know how to construct them. So that's one big application. Another application is also to the local Langlands correspondence. So the idea of the correspondence, the idea of the local Langlands correspondence is that to every representation of a p-adic group, there should be some number theoretic parameter attached to it, which is a Galois representation roughly. And so if you want to do this explicitly, you better know how to write down these representations explicitly so that you can then attach the Langlands parameters explicitly to it. There are also applications to automorphic forms. So automorphic forms are generalizations of modular forms, which played an important role in Fermat's last theorem, for example. If you want to study these, it's also helpful to study representations of p-adic groups. You can deduce properties about automorphic forms from there. So for example, I have a joint work with Sorgushin where we prove properties about these representations of p-adic groups explicitly and then deduce properties of these automorphic forms. We show that there are particularly nice automorphic forms that one can work with easier. And that also has applications to a global Langlands correspondence. Which, as I said, is tightly related to generalizations of Fermat's last theorem. There are applications to the p-adic Langlands correspondence. There are applications to crazy things like mirror symmetry. Don't ask me for the details because, unfortunately, I do not know all the details, but I just know that Lam and Tim Gle, they have some important work in that area. They came to me and asked me about all the details for these constructions of where are they, these representations, because they needed that to prove instances of the mirror symmetry conjectures. Yes? Again? The name? Thomas Lam and Niklas Templé. So they have an interesting paper on that topic. And so I think the idea of this mini course is also that maybe some of you find new applications. So I try to give you some indication of what are the results that we can obtain, and then you can see if you can maybe apply that in your area as well. All right, so that's the first goal. Let's see, what time is it? Excellent, okay, so I want to say now a few more words to actually tell you what are these supercuspal representations and to tell you what it means that they are the building blocks. And then I will tell you how to describe the whole category of representation in terms of these building blocks. And we'll take maybe a short break as well. And then I move on to giving you some examples of how these objects look like and a better idea of how the whole category looks like. All right, so, and maybe we should also see some examples. We haven't seen much examples yet. So let's see. The next important thing is if we want to try to understand these building blocks and how to construct representations is to talk a bit about parabolic subgroups. So here's a definition. Parabolic subgroup of GLN, or also of all the other groups I've written down, of SLN, or SP2N, or SON, is a subgroup of the shape. It's a block upper triangular matrix. So we take all the matrices where we choose some blocks, whichever size of blocks you want. And you're allowed to put anything you want on these blocks. And you're allowed to put anything you want above these blocks. And everywhere else below these blocks, you have 0. Everything else is 0. So that's what a parabolic subgroup is. It's a block upper triangular matrix, but you're also allowed to conjugate that by some element inside the group G. So you're allowed to conjugate this around. So where, I I should say G is some element in our group G, for example, GLN. And we have fixed the choice of blocks. So we have fixed these blocks. So in other words, we have fixed the decomposition of n into summons n1 plus n2 plus and so on, where the first block has size n1, the second block has size n2, and so on. So that's what a parabolic subgroup is. You fix some block sizes, and then you take all the matrices of this following shape. And what's the nice thing of it? Well, the nice thing is we can use this to construct representations. But let me say one more thing that's particularly nice is there's a Levy decomposition. But if we take such a parabolic, let's say one block, another block, and a small block. So that's a parabolic subgroup. Then we can write this as a product, and we can take the blocks apart. So we can first just take the blocks. Oops. These are supposed to be the same blocks as here. And take only matrices with entries in the blocks and 0 everywhere else. And then afterwards, we can take just the upper triangular thing. So we take the same blocks. And now we take just ones on the diagonal and 0 everywhere else, and take whatever you like in the upper part. And I said everything can be conjugated by G, so I should actually really conjugate everything by G. So that's what's called the Levy decomposition. So we have a product of two subgroups. So let's call this parabolic is often called P. So that's P. This first group is often denoted by M. M is called the Levy subgroup. And this last group is often denoted by N or U. And this is the so-called unipotent radical. What is the unipotent radical? It is the maximal connected normal unipotent subgroup of this big group P. What is a unipotent subgroup? A unipotent subgroup is one of that shape exactly. It's one with ones on the diagonal, something above the diagonal, and nothing below the diagonal. If something embeds into upper triangular matrices, well, ones on the diagonal, it's called unipotent. And so this is the maximal connected normal unipotent subgroup. And that's actually back where we started with when I said reductive groups are those whose unipotent radical are trivial. So you see that the parabolic is not reductive. On the other hand, M is a reductive group. So this M here, this is again a p-adic group. And it is just the product, in the case of GLN, it's just the product of GLNs. In the case of the other groups, it will be a product of GLN with some of the other types of groups. And so that's the Levy decomposition, that we have a unipotent radical, which is a normal subgroup, semi-direct product, with a Levy subgroup, and the Levy subgroup is again a p-adic group. And so why did I do this now? So I started with my p-adic group G. Inside there, I found this parabolic group. And inside there, I found again a p-adic group that is of the shape as we know it already, just the products of GLNs, for example. And so this is really helpful because now we can start with representations of this smaller p-adic group M and build from there representations of the larger group G. And so that's what's called the parabolic induction. So let me define that for you. And that's now our first example of how to construct explicit representations. And that's something people knew already 50 years ago. So the parabolic induction is the representation, let me call it in from the parabolic subgroup to the whole group of, say, I need a name for representation, say sigma, and the space V sigma for parallel representation for a given representation sigma V sigma of the representation M. So this parabolic induction, maybe the sentence doesn't make sense. The parabolic induction, which I denote by this parabolic induction in from P to G, for a given representation of M is the following. So the space of this representation, what is the space? The space just consists of functions from the group G to this representation space V sigma with the following two properties. So somehow we need to make use of this representation on P. So it has the property that if I evaluate f on M and G, for M being an element of my Levy subgroup and N being an element of the unipotent radical, then this is the same as just, oops, need a bit more space. So let me write this further down. And G inside G is the same as applying this representation sigma to M, nothing to N, the unipotent radical, you just ignore it, and then take f of G. So that means any element, something in the parabolic subgroup on the left gets pulled out via this representation sigma. That's the first condition. And the second condition is we want it to be a smooth representation, and this is ensured by saying that there exists some compact subgroup K sub F, so that's some compact open subgroup of G such that f of gk is equal to f of g for all small k inside this capital K G that's attached to f. So the second one is guaranteeing smoothness, and the first one is this property, what it means to be inducing from a representation of M, so we know what it is on N, and therefore also on the parabolic P, and we get a representation of the whole group G of it. So that's the space. So it's roughly functions on G mod P. And what is the action? So the action is as follows. So the action, so this is the name of the representation. Now I need to tell you what it is if we apply it to G being some element in G. So this is by definition something that lies in the space of automorphisms of this big vector space. And what is that? Well, what happens if I apply this to a function f? What happens is I get back the same function except that I plug in G on the right. So it's so-called right translation. So what is this function? This function is the function that takes an element x and sends it to fxg. So it's everything right translated by G. So this is a representation. Let me give you a very explicit example. So here's an explicit example. Let's take G to be SO2 over QP. And let's take, as my parabolic, I take the upper triangular matrices. So the blocks are just these one entry blocks, one by one blocks. And so that means as my M, I just have the diagonal matrices. So they look like T inverse because I know that I'm in SO2. And so now I need to take a representation sigma V sigma of M. And I want to take this to be the trivial representation acting on the one-dimensional vector space. So that means trivial representation applied to a vector is just equal to 1 inside C star, which is just GL1 of C. So we just don't do anything. For every element of M, trivial representation of M just does nothing on this one-dimensional vector space. And then the parabolic induction from this parabolic subgroup to the whole group of this representation sigma sigma, let me write the vector space V sigma of that. These are just by definition functions now from SL2 of QP to this one-dimensional vector space C that have the property that they transform on the left via sigma. Sigma is the trivial representation. So in other words, these are just functions on the quotient SL2 by this P, by these upper triangular matrices. So these are just functions on the quotient. And then we have the condition, the second condition about this compact open subgroup, which just translates into F being locally constant. So that's just another way to say that there exists this compact subgroup that satisfies the property that it doesn't change the function on the right. And then I just act on this space via right translation. So that's one example of a smooth representation. So this gives a smooth representation. I should have said that the parabolic induction, so this is a smooth representation. This is a smooth representation. So that means in this way we can construct a lot of smooth representation just via parabolic induction. And that's what people knew around 50 years ago already. They knew how to construct all these representations. And now what are the supercuspal representations? These are exactly the ones that we can't construct in this way. So let me give you the definition of supercuspal representations and the fact about them and why they are building blocks, and then we take a short break. So here's the definition. A supercuspal representation of our group G is an irreducible representation. So irreducible means has exactly two subrepresentations. So subspaces that are preserved under the action, which are the trivial one. So just this, not even the trivial, sorry, which is just the zero space and the representation itself. Well, let's call this pi v. And let's give this a name, a supercuspal representation, pi v of G is an irreducible representation of G such that it satisfies the property that this representation pi v does not embed into a parabolic induction of some other representation for every proper parabolic inside our group G. And we can write this again as semi-direct product. Oops, I've written the semi-direct. Oh, no, it's fine. For every parabolic subgroup and every representation sigma v sigma of M. So once more, a supercuspal representation is an irreducible representation that does not embed into a proper parabolic induction. So we can construct a lot of representation via parabolic induction, but we can't construct the supercuspal representations. So for those, we have to find a different way of constructing them, and that's what I'm going to talk about in this mini course. And here's the fact of why are they the building blocks. So if pi v is an irreducible smooth representation of G, then there exists some parabolic subgroup inside G, which is the semi-direct product of Levy times the unipotent radical, and a supercuspal representation sigma v sigma of this Levy subgroup N, such that the representation pi embeds into the parabolic induction of this representation v sigma. So that means all the irreducible representations can be obtained from the supercuspal representations via parabolic induction. And note that here I say P is a parabolic inside G that might be equal to G. So in the case that pi is supercuspal, P is equal to G, and this parabolic induction just doesn't do anything. So the supercuspals are the ones that don't embed into proper parabolic induction, but all representations, all irreducible, embed in some parabolic induction. So that means these supercuspal representations, they are really the building blocks, and they are now the missing piece. After I've told you we know how to do parabolic induction, the missing piece is really to understand these supercuspal representations, and then to understand how we can parabolically induce from there to get everything. All right, let me take a 3-minute break so that you can just relax for a few minutes, and then we'll try to answer these questions. So it's 11:04, so let's say 11:07 we continue. All right, so what did we do before the break? We talked about what are the p-adic numbers, what are p-adic groups. We talked about what is the representation of a p-adic group. Then we learned that all the representations are obtained from parabolic induction, from supercuspal representations. That was this last statement here. Every irreducible representation embeds into the parabolic induction of some supercuspal. And so now there are two questions that remain. The big question is, what are these supercuspal representations? That was our first goal, to construct all of them. And I want to show you some of them in a bit, but before I do that, I want to say a few words about how can we use this to describe the whole category of all representations. And so that's something, so I'm basically going a bit chronologically, so parabolic induction, and so this was, the whole story was done around 50 years ago, and then Bernstein observed, I think in the 80s, the so-called Bernstein decomposition, that which we call now Bernstein decomposition, which is the following. So what we aim to understand is the whole category, that's the category of smooth representations of our group G. That's, well, I defined what smooth representations are. I have to define also what morphisms are between these representations. Morphisms are just vector space morphisms that preserve the action of G. And so we want to understand this whole category now. And so we can do this using that we know that all the irreducible embeds into the parabolic induction, and that gives us a decomposition of the whole category into so-called Bernstein blocks. And they are indexed by M and sigma. What is M and sigma? Well, M is a Levy subgroup of a parabolic subgroup of G. So this is the same as the same M that's over there when I write, well, that I erased, I think, that was written here when I wrote P equals Mn. Sorry, Mn, semi-direct product. And sigma is a supercuspal representation of the Levy subgroup M. And so we know that every irreducible appears in some parabolic induction, and that's how these blocks are created. So the blocks are created by just taking the parabolic induction, so P is this Mn, to G of the sigma, and then taking just everything that is contained in here. So everything that is all the sub-quotients of this representation and putting them together in this block. And so to make this more precise, everything that's in here are all the representations, all of whose irreducible subquotients are subquotients of this parabolic induction. So that means you just take this parabolic induction, look at all the subrepresentations and all these quotients thereof, and collect all of that together, and that's what builds the Bernstein block. To make this precise, if I really want to get everything in there, I also need to put a little prime here. And what does the prime mean? The prime just means that I take this up to an equivalence. So I take this over a whole equivalence class of all M prime sigma prime that are equivalent to M and sigma. And what is this equivalence? The equivalence is that M and sigma is equivalent to other pairs that have the following shape. So what can we do? Well, we can conjugate everything by just an element G inside our group, and then we have to conjugate the representation accordingly. And then we get a different levy with a different representation, which is just the conjugated of it. And if we parabolically induce that, we end up in the same Bernstein block. So that's a very natural relation that you would guess. And also, for some technical reasons, we have to twist it by some character phi. We are allowed to twist it by character phi, and phi is a so-called unramified character, which means it is a character which means a one-dimensional representation of M that is trivial on all compact subgroups. Trivial on all compact subgroups. This is something very technical. I urge you to just ignore that for now. So really what you should think of is a Bernstein block is everything we obtain by parabolically inducing the sigma from a parabolic containing M. And then we just collect everything together, and that forms the block. So these are actually the blocks. They are indecomposable. You can't decompose them further. And let me maybe write this in red. That's called a Bernstein block. So this is a Bernstein block. So that tells us a lot about the category. The category decomposes into these blocks. It's a direct product, so that means if you take an arbitrary representation, it decomposes into a sum of representations, one inside each block. And the interesting things, the non-trivial extension, they just happen within a block. So this is very abstract. So let me follow up immediately with an example so that we actually see what's going on here. So let's take the example that G is equal SL2. There are two interesting cases of, well, there aren't that many parabolic subgroups. The two cases are that the parabolic subgroup is just the group G itself, and then the Levy subgroup is also the group G itself. In that case, we are looking at a block indexed by M being equal to G and sigma being a supercustal representation of G. And here's the nice thing that happens. All the objects in this block are just sigma and sigma plus sigma, sigma plus sigma plus sigma, and arbitrary direct sums of sigma. So there are no interesting extensions of sigma with itself. So this is a rather nice and easy block, up to we still need to understand what sigma is. So that will be a subject of what I'm going to speak in a moment, to understand how do we construct sigma. But once we construct sigma, this block is really easy to understand. Here's the second example if P is these upper triangular matrices, so where the blocks are one-dimensional on the diagonal, and then M is just the torus, is the name, the diagonal matrices. The name for that is a torus, so one often also writes T for torus, just the name for the diagonal matrices. And in that case, let me just take sigma to be the trivial representation. So that means V sigma is just the one-dimensional vector space, and the action on it is just trivial. Nothing happens. In that case, the block that's attached to this T and sigma is much more interesting. This block actually has a name. It's so interesting that it has a name. It's called the principal block. And so how can we understand what's in the block? Well, I said we need to parabolically induce. So we need to parabolically induce from these upper triangular matrices to the whole group the trivial representation. And we need to understand what's contained in there. And so some exercise that you can check that actually the trivial representation is contained in this parabolic induction. And there is a quotient that is non-trivial, and this quotient is just called ST, which stands for Steinberg. So that's the Steinberg representation, which is just defined to be this quotient. And so that means this principal block contains, in particular, the trivial representation and contains the Steinberg representation. So we see that this block contains two different representations, and there's some non-trivial extension thereof. So something more difficult is going on there. And so that's the second goal, to understand these blocks. So goal 2 is to understand these Bernstein blocks. Understand how they look like in full generality. And so here's the spoiler. So here's the result. Let me say it's in vague terms. Because I want to write down the result already so that I can motivate why we care about. Well, first of all, we of course care about understanding the category of representations. In particular, if we want to upgrade things to a categorical version. So people like to, so traditionally people look at explicit local Langlands correspondence, and recently it became fashionable to look at categorical local Langlands correspondence. So try to upgrade everything to a categorical level. And so if we want to upgrade things to a categorical level, then we want to understand the structure of the whole category, not just of the building blocks. But there's more motivation to trying to understand these blocks. And so here's the result in vague terms. And I should mention that this is joint work with Jeff Adler, Manish Mishra, and Kazuma Ohara. And that's in progress, which is the following statement. Statement a priori is still a bit confusing, so I'll explain this in a moment. So if we take an arbitrary Bernstein block, then this is actually equivalent to a Bernstein block where I add a 0 everywhere. So I add a 0 to the G, to the M, and to the sigma. And what does it mean? It means that this is actually a so-called depth 0 representation. And depth 0 representation I haven't defined for you yet, but I will talk about them in a bit. They will be subject of this course. And they correspond to representations of finite groups of Lie type, at least up to center. So depth 0 means corresponding to representations of finite groups of Lie type. So the problems are now reduced to questions about representations of finite groups that are often much easier to tackle. And so this equivalence, what is this? So I say an arbitrary Bernstein block is equivalent to this Bernstein block corresponding to some depth 0 representation. And the crucial part about this is that this block here is much better understood. So let me say rather well understood. Already for a long time, so for example, Morris had some important work in '93 on that, and we extend this further. So I will explain more what we know. I mean, we know that this is equivalent to the category of modules over a nice algebra, and we can describe this algebra rather explicitly. So that's something well understood. And that means, in particular, maybe I can write this down here as application. So why do we care about such a result? So there are two reasons why we care. First is, since this is well understood, we now understand essentially all Bernstein blocks. So that's one result. We want to understand all Bernstein blocks. And the second thing is, not only do we now understand all Bernstein blocks, but we know that they reduce to these depth 0 blocks. And here a lot of things are much easier. So we can use this result also to reduce a lot of questions for arbitrary representation to so-called depth 0 representations where things are much easier. So one application is that can reduce many questions that you can ask about the representations also in the classical setting. So many questions about representations to depth 0 representations. And so the nice thing about depth 0 representations are that they are much easier to deal with often, which are easier or already known. So the questions about depth 0 representation, they might already be solved. So you can now solve questions about all the representations by going to depth 0. There you know the answer, and then you deduce back the answer to arbitrary representations. Or you want to prove something new, reduce it to depth 0, and then realize that there it's much easier to solve, and then you solve the problem there. Okay. And so these are the two big things that I want to talk about in this course, which is the construction of supercuspal representations is the first one, and the second one is, once we have these supercuspitals, how does the whole category look like? All right. Let's see. Are there any questions about the broad picture so far? Yeah. Why do we call it depth zero? That's an excellent question. Okay, let me give you an answer now, and then you'll see it in a moment again. So I said smooth representation means that every vector is fixed by some compact subgroup. But we don't know by which one. And I've written at the beginning this sequence of smaller and smaller compact open subgroups that lie inside GLN. So all these matrices that are congruent 1 modulo p to the n. So that's a sequence of subgroups that get smaller and smaller and smaller. And so Moy and Prasad in general generalized this and defined a lot of sequences of compact open subgroups that get smaller and smaller and smaller. And so now if we take an arbitrary, smooth, irreducible representation, we know it's fixed. There's a vector fixed by some of these compact subgroups, but we don't know by which one a priori. And so the depth of a representation is what Moy and Prasad then defined to be the largest subgroup under which we have fixed vectors. And so then the depth could be either 0, which means something is fixed under just a subgroup that is slightly smaller than the maximal one, or it could be positive depth if you have to go further down in the filtration. So that's the notion of the depth. How far do we have to go down? And the depth 0 representations that I mentioned here are the ones that have depth 0, so that's the smallest possible depth that they can have. So these are the ones that arise from a maximal compact subgroup and that are trivial on just the next subgroup. And these are the ones that come from representations of finite groups. Excellent question. More questions at this point? All right, so then let's see if I have a nicer piece of chalk. So the two goals are clear, I hope. Now I want to go back to goal 1, which is the construction of supercuspidal representations. So here is the big folklore conjecture. So far I've only shown you how to construct smooth representations other than supercuspidal representations, and they were really difficult to construct. People didn't know how to construct them for a long time. And I want to show you how one can construct them and show you an explicit example in just a second. So here's the folklore conjecture. All supercuspidal representations are of the following form. They are of the form compact induction from K to G. I say in a moment what this is, of a representation rho. So where, and I say in a moment what this is, so where K inside G is a compact mod center open subgroup. Compact mod center open subgroup. So it includes it always has to include the center, and if you mod out by the center, it's compact. So the center is just something annoying in the way. And rho, V rho, is an irreducible, smooth representation of K. And since K is compact mod center, this is actually a finite dimensional representation. So what I haven't said yet, but what you might have observed, is that usually these smooth representations of p-adic groups, they're usually infinite dimensional. So when I wrote down these parabolic inductions, these were functions on roughly G mod parabolic P, and this was an infinite space, an infinite quotient. So these representations are usually infinite dimensional. And so if you restrict to a compact subgroup, they become finite dimensional. And so starting with a compact open subgroup, compact mod center, and the representation thereof, we can compactly induce that representation, which is, what is this? It's similar to parabolic induction. These are all functions from G into the space V of rho that satisfy the property that, let me write it here, f of k g is equal to rho of k f of g for k, small k and capital K, small g and capital G. So that's the standard induction condition that we have seen already before for parabolic induction. And then compact induction means that f is compactly supported. The smoothness condition is automatic, so I'm not writing it this time. So these functions should be all compactly supported mod center. So that's the compact induction. So it's very similar to parabolic induction, except we don't induce from a parabolic subgroup, but now from a compact subgroup. And the folklore conjecture is that all superclassical representations arise in this way as the compact induction. So that's the conjecture. Here's an, or maybe I can fit it down, an explicit example. Let's take G equals SL2. It's my favorite example for the blackboard because it's something you can actually write down on the blackboard. Let's say SL2 of QP. Feel free to take any other field you like, any other p-adic field. And I need a compact subgroup. So as my compact subgroup, I take the subgroup that contains plus minus the identity. That's the center. That's just for technical reasons. The center has to be there. And then I take all the matrices that have the following shape. They look like 1 plus PZP on the diagonal, and ZP and PZP off diagonal. And since it's an SL2, the determinant is equal to 1. I will not write this all the time. When I write matrices like this in SL2, that means determinant equals 1. So that's my compact subgroup. And now I have to define for you this representation rho. So, or first of all, what's V rho? As V rho, I just take the one-dimensional vector space C. And so that means now I have to define for you a representation rho, which is a map from K to the automorphism of C. So that's just GL1 of C. So that's just C star. In other words, it's a character. And so how does this rho, is this rho constructed? We have to construct something on these two things. So let's say rho takes this plus minus identity and just sends it to 1 inside C star. So just the trivial representation, nothing interesting, because I don't really care about the center right now. More interesting is what does rho do to this matrix 1 plus PZP on the diagonal and PZP and ZP off diagonal. So here's what I can do. So this is some nice compact subgroup. And I knew I want a smooth representation. So it has to be trivial on a smaller compact subgroup. And I just force it to be trivial on a rather large, smaller subgroup. So let me rewrite the same matrix. I wish I had an iPad now that I could just copy paste. So that's just the same, and I quotient out by something just slightly smaller. And what do I quotient out by? I quotient out by the matrices that are the same on the diagonal, but off diagonal, they are slightly smaller. So I'm just increasing the order of P off diagonal. So I change the ZP to PZP and PZP to P squared ZP. So what does it mean? So this quotient now is just isomorphic to, well, the diagonal, it's just killed, and the off diagonal, I just have ZP mod PZP, which is just a number between 0 and P minus 1. So that's just something of the finite field with P elements. So this quotient is isomorphic to just matrices with FP on the off diagonal and 0 on the diagonal under addition. And now I'm running out of space, so let me continue over here. So let me write down this matrix once more. So it's 0 on the diagonal, FP off diagonal. So I've now mapped to this matrix. And I need to map this further to now some complex number is the goal. So if I take a matrix AB, what can I do? Well, I can map this first of all to just some element in the finite field by just summing A and B. now I have an element of a finite field, and I want a complex number. Well, it's like somehow I need to map it to the complex numbers. And I just map this to the p's root of unity times raised to the power a plus b. So this is a number between 0 and p minus 1. So I can map it to e to the 2 pi I mod p. So p's root of unity to the power a plus b. And so that way I now obtain a map from this compact open subgroup here, this k, to the complex number over there. So I obtain this map rho from k to GL1 of c. And that's now my representation that I can compactly induce. So I can now build my representation, say pi sub rho, by just compactly inducing from k to g this representation rho that I've just constructed. And this is now an irreducible supercuspidal. Well, I said supercuspidal means automatically irreducible supercuspidal representation of SL2 QP. This is a particularly nice one. It's even called simple supercuspidal. It was constructed by Gross and Wieder earlier. It's also an example of an epipelagic, so-called epipelagic supercuspidal representation constructed by Gross and Wieder. So this is a nice, easy example that appears over and over again.
Sorry, I'll interrupt you.
Sure.
So, just switch down. Okay, that's perfect.
Can you hear me? Is the mic on again? Is it working?
Yeah, it's okay.
Okay, excellent. So here's our first example of a supercuspidal representation, compactly induced from some compact mod center subgroup of some nice representation. And so the goal of this course is to understand much more general constructions, to generalize this, to obtain all supercuspidal representations. So let me give you an overview of what is known. So the conjecture is known for the following cases. It's known for the case that G is equal to GLN of your favorite p-adic field, your favorite non-Archimedean local field. That was work started here with Howe and Moy like almost 50 years ago. I think it was finished by Bushner and Kutzke about 30 years ago. It's also known for classical groups. Classical groups are fixed points of an involution, so this means symplectic group and orthogonal group and unitary groups. I haven't talked about unitary groups yet. This is known in the case that P is different from 2. That was done around 15 years ago by Sean Stevens. And the idea is to basically imitate what one has done for GLN and use that these groups are sitting nicely inside GLN in the sense that they are just a fixed point of an order 2 automorphism. So I said in general, think of reductive groups, the p-adic groups, as nice subgroups of GLN, but these are even nicer. They are particularly nice. And it's also known for inner forms, so-called inner forms of GLN. So that means GLM of some division algebra. D is a division algebra over the field F. So that's something that becomes isomorphic to GLN over a field extension. So there are notion of base change. So you can base change to essentially tensor this group over F with some big field extension, and then it becomes isomorphic to GLN. And so these cases are known. They are all done in a classical sense using GLN, where you can understand things rather nicely. And what I'd like to focus on is what is known in general. So for general G. Oh, I should have said the inner forms, that was work of Sécher and Stevens. And a lot of people have worked on this. A lot of people worked on special cases. So yeah, I think it's impossible to make an exhaustive list here. So what do we know for general group G? So I was asked already, what is the depth? And I said the depth could be either 0 or it could be a positive real number, and I'm like to draw this now. The depth is either 0 or positive, depending on how far you have to go down in the filtration that I'm going to talk about in the future to get fixed vectors. And so now I want to draw in this direction the prime number p, because some of the results depend on what the prime number p is. And so the first result was 1994-96 by Moy and Prasad. They introduced this notion of depth, and what they then did is they studied these depth 0 representations. So they studied the depth 0 representation and said that they correspond to finite groups of Lie type. And I should say that Morris tried to do the same roughly around the same time, and there's a paper from 1999 where he does it in using a bit different approach. So that's the depth 0. And then people try to go deeper down in the ocean. Let's see, I've limited short color. And so then people try to construct representations that I'm now just writing as circles deeper down. And so that happened around 1998. Jeff Adler in his PhD thesis gave a construction of representations of positive depths, something that is a bit like the one that I've just given to you. And then that was Jeff Adler, and then JKU generalized this construction vastly in 2001 and constructed a lot of representations. And this is the construction that's the most general that's known to date. And this is the construction that I want to explain a bit in this lecture series, not today, but in future talks. It's somehow an amalgamation of the depth 0 representation that I haven't talked about yet, together with this example of the character, but making things a bit more complicated. And then the question was, well, do we get everything or not? And in 2007, Julie Kim actually proved that under the assumption that the prime p is very, very large, so if we are here where p is very large, then we get everything under the assumption that the characteristic of the local field is equal to 0. So that means, as we have learned at the beginning of this lecture, that means f is a finite extension of QP, but f is not the Laurent series over a finite field. But I've said earlier that the Laurent series over a finite field behaves so similar to these finite extensions of the p-adic numbers. So we want somehow to get the same result. And so that's what I've done in, use the same color, 2021, is to remove this condition so that it now holds also for arbitrary fields, so for arbitrary non-Archimedean local fields, so also for function fields, for finite local function field, finite extensions of the Laurent series over a finite field. And I also improved the bound so that we get exhaustion in a much larger region, only under the assumption that p is large. And by p large, I mean p doesn't divide the order of the Weil group. And what is the Weil group? The Weil group, well, it's something attached to the p-adic group, and for GLN, the Weil group is just the group on n letters. For classical groups, it's something similar. So that means essentially for classical groups, for all the groups that we have seen, we want p to be larger than n. That's the condition here. So roughly, let me write this as p greater than n, where n is the n in GLN or SON and so on, SP2N. And so that leaves two more questions. Well, at least one more question. Well, one question is, how do we do this? And that's what I'm trying to show you in this course. So the course will be about this result. And then the other question is, what happens for small primes? And so here, we can actually construct a few more representations. A few more representations of small depths have been constructed earlier by Vida and Lieu, together with some input of myself and something of Beth Romano. And what I'm currently working on, so that's work in progress, doesn't have a year yet. Work in progress is, together with my postdoc David Schween, we construct new representations of arbitrary depths. And obviously it has to be for small primes, because for large primes everything is already constructed. So small primes, we construct some new representations that are missing so far in the hope to fill in the gap. And so this is the picture that we are at today. So if P is, say, greater than N, then we know how to construct everything. And for small p, it's work in progress. And as I said, that will be subject of this course. All right. See how I'm in time. Excellent. Any questions so far? All right. So that's the answer to my goal 1, which is to construct all these supercuspidal representations. The second goal was to understand the whole category. And so, since today should be a bit an overview talk about everything, essentially, I want to tell you also a bit more about this second step. So the second step is done via so-called type theory. So I should tell you about types. And these types is actually also what has a lot of different applications. So for example, I mentioned applications to automorphic forms, and that actually comes via the theory of types. A slightly different theory than the one I'm introducing right now, but a related theory. So here's the definition of a type. So before I write this down, we know now that the supercuspidal representation, they are all constructed via compact induction from some compact mod-center subgroup of some representation. The idea of types is now that we want to understand all other representations, also using compact open subgroups and representations thereof. Because somehow that's much nicer, much easier. We have a compact subgroup, then we know that the representations are finite dimensional. It has something to it. And also you'll see in a moment why this is powerful. So here's the definition. A type is a pair K, rho. And rho really stands for rho and v rho. It's a representation of K. So this is a representation of K. But I start dropping the space and just write the rho. It's common that one drops one of the two objects. And so K is a compact subgroup of G. And you see compact subgroups appear quite often, so that's why we need to study these compact subgroups as well in this course. So a type is a pair K rho such that, and let me say it's a type, let me say an M sigma type. So let me give this a name, M sigma, where M is a Levy and sigma is a supercuspidal representation of it. And M sigma type is a pair such that for every irreducible smooth representation pi of our group G, the following two things are equivalent. The first statement is that the representation pi is contained in the Bernstein block of M and sigma. And the second statement is, and these two should be equivalent, the second statement is that this can be detected from K. So the second statement is that if I take my representation pi and restrict it to K, then it should contain the representation rho. Or in other words, the space of homomorphisms, of G homomorphisms from V rho to V pi, so from the representation rho to the representation pi, is non-trivial. So there's some non-trivial homomorphism which corresponds to this inclusion. So rho is usually, let me say this, an irreducible representation. So we can map rho into pi if and only if pi is contained in this Bernstein block. So that means K rho is a type if and only if it detects if a representation is in the Bernstein block or not. So something is in the Bernstein block if and only if the representation contains rho. So So for the examples we had before, that might fit down here. So in the case of SL2 of QP, we had two examples previously. The example A was our supercuspal representation, and if our supercuspal representation was the compact induction, then this corresponding pair K and rho is a type. So K rho is a type for the group G together with the representation pi rho, which is just the compact induction from K to G of rho. So if we have a compactly induced representation, the inducing datum is just the type for it. And the second case that we had was the case with the diagonal matrices and the trivial representation thereof. And in that case, as compact subgroup, we just take the matrices of the form ZP, ZP, PZP, ZP together with the trivial representation. And that is a type for, or I guess I should write it the other way, a type for the diagonal matrices, this T, T inverse, together with the trivial representation. So these are two examples of types for the two Bernstein blocks that we have encountered earlier. This is how we can detect if we are in the Bernstein block or not. And why is this so interesting? It's so powerful because of the following theorem by Bushnell and Kutzko. From 1998. So they studied these representations of GLN and then tried to make sense of what they constructed by introducing this type theory. So that's what they introduced. And here's the nice theorem that says, suppose K rho is an M sigma type. So it's something that detects this Bernstein block. Then this Bernstein block attached to M sigma is actually rather well understood. Subject to understanding one more object. This Bernstein block, this category, this block, oh, it's got erased already, this block that forms a block of our category of all smooth representation, this is equivalent to modules over something that I call H of G K rho, and I'll say in a moment what this is. So it's equivalent to write unitary modules over this object H. And what is H? H is a Hecker algebra. So Hecker algebra is a term that's overused, but we call this a Hecker algebra. And what is this? It's something very explicit. These are just functions. And now we call the compact induction that I just erased, it's very similar to this. It's functions from the group, but not to the space of rho, but to the space of endomorphisms of this complex vector space of rho. And now the property is that this function transforms not just on the left, but on the left and the right via this representation rho. So f of k1 g k2 is equal to rho of k1 f of g rho of k2. Again, ki's, small ki's in capital K and g, small g in capital G. And also, f should be compactly supported. So you see the definition is very similar to the definition of compact induction. And that's not a coincidence, because another way to define it is that it's an equivalent definition. This is actually equivalent to just the G endomorphisms of the compact induction from K to G of this representation rho. So these are two compatible definitions, either explicitly in terms of functions or abstractly as the space of G endomorphisms of the compact induction. Here you see automatically easily the algebra structure is just composition. Here the product is defined by a convolution. That's just some integration formula. One can write it down, but I don't think you gain much by me writing this down right now. want to keep that picture. So, theorem was now, suppose we have types, then we understand the Bernstein block subject to understanding what the Hacker algebra is. So there are two questions now that you might wonder. First of all, do we have types? If we don't have types, then this statement is useless. And then, what is the Hacker algebra? The first answer is, yes, we have types. So, types exist. And now I'm actually just reusing this picture in all the cases on the right. So in all these cases. So whenever we have supercuspal representations, we also have types. So that was done shortly afterwards. So that maybe I don't have much color. So if I want to add types, I should add Julie Kim's name here. She observed that use construction also produces types. And for classical groups, I should add Miyuchi did it together with Sean Stevens. Otherwise, it's the same people, essentially, that did it. I guess I should also put my name there for fixing a few gaps in the literature. And so that means that if we want to construct types, if P doesn't divide the order of the Weil group or is larger than N for GLN and similar groups, well, GLN, we know it anyways, but in that setting, for general groups, we have types if P doesn't divide the order of the Weil group. And they were constructed by JKU together with Julie Kim that observed that the same construction essentially works as well. And so that's something I'm going to talk about in this lecture series to try to explain a bit how does the construction of types work. And so now, I was told I can do whatever I want and go on for hours, but I think I should stick to the 2 hours that were announced. So I have another 7 minutes roughly, so I want to just state the final result that I alluded to earlier, and then the next lectures will go into more details. So here is the result. It's two theorems. Theorem 1 is the one that I mentioned earlier, together with Jeff Adler, myself, Manish Mishra, and Kazuma Ohara, which is in progress. Which is, I said, now we know that there are types, so the remaining question is, when do we understand what this Hacker algebra here is? If we understand the Hacker algebra, then we understand the Bernstein block. And so our result that is currently in progress is, let me make this precise, so let K rho be a type as constructed by Kim and Yu. So that's this construction in red here that is exhaustive if P doesn't divide the order of the Weil group. So they exist in this large general setting for some Bernstein block M and sigma. Then the claim is that there exists the following. There exists a G0, a subgroup of G, a smaller p-adic group. So that's also a p-adic group. Subgroup, a p-adic subgroup. And inside G0, there exists M0, a Levy subgroup, so a Levy subgroup of a parabolic subgroup. And there exists sigma 0 v sigma 0, a depth 0 representation of M0. And finally, there exists a type for that. So there exists a K0 and rho 0 and M0 sigma 0 type. Such that, so that was a lot of notation, but here's the summary of the notation, such that the Hacker algebra constructed from GK and rho, so that's the one we started with that we want to understand, is isomorphic to the Hacker algebra constructed from some smaller p-adic group and some type of the smaller p-adic groups that correspond to a depth 0 supercuspal, depth 0 representation. So that's a depth 0 type. So this statement is somehow completely useless to you because I haven't really told you anything about that yet, the depth 0 part. So we really need theorem B, which is due to essentially Morris from 1993. And I should also add our initials there because Morris only states the result for union of Bernstein blocks rather than a single Bernstein block. And that says that we understand explicitly what this Hecke algebra is. And we can describe it rather explicitly. So this is a semi-direct product of some twisted group algebra, of some omega, let me call this omega of sigma 0, with some twist in it. You can ignore what the details is. The real statement is there exists an explicit description in terms of a semi-direct product of some twisted group algebra together with some affine Hecke algebra of some affine Weyl group with some parameters. So whatever these objects are, I'm going to explain this a bit later throughout the course. Really, the takeaway is there exists an explicit description of this object. So that's really what I want. So, i.e., exist explicit description of this object on the right, and thereby also of the object on the left. And so, in the final minutes, I just want to give credit to everyone. Keep the picture. So, of course, use construction has been around since the early 2000s, end of the 90s, and it was rather quickly realized that one gets types the same way. So this question has been around for a long time. So we are not the first ones to study this. And so let me say theorem A for general G has previously proven for the case of, or maybe let me first say, in the case of GLN, theorem A was already known thanks to Bushnell and Kutzko, and people also worked on classical groups and special cases. But for general G, well, not that much has been obtained. So the two cases that have been previously obtained is the extreme case that M is equal to, I often call it T, is a maximal torus that is also split, so a split maximal torus. What does that mean? It just means M is equal to the diagonal matrices. So all the blocks are size 1. So this case has been obtained previously by Roche. I think that was 1998. I should have double checked and put a small question in the 90s for sure. And the second special case is the case that M is equal to G. So that's the case of supercuspidal representations that has been obtained by Kazuma Ohara in 2021. So these two extreme cases where we have block size 1 or where we have M equals everything, this has been obtained previously. These are in some sense the easiest two extreme cases. And now what we obtained is the full general result for all possible M or possible sigma with no conditions at all, which as the final, I still have a minute, final corollary is the thing that I've mentioned earlier, that if we take an arbitrary Bernstein block, this is equivalent to a depth 0 Bernstein block. And therefore, a lot of questions can be reduced to the depth 0 questions. And this is something that we will also try to study a bit in the course. So I will define for you depth 0 representations explicitly and tell you what I mean with they correspond. I guess it got erased that they correspond to representations of finite groups of Lie. All right. I will, at some point, write abstracts for the next 3 talks and post them online so that you get an idea of what the next 3 talks are about. And I'll stop here for today, so you can ask more questions if you like. Thank you.